Hello, and in today's ATmega328P programming, we are going to set up a timer base. So let's have a look at the schematic. The schematic is effectively the same one as the previous tutorial from the ADC. We still have the 8 LEDs that we use for a display output. And then we are going to use the analog pin with the 10K pot. And the 10K pot is going to set the blinking intervals of our LEDs based on the internal timer. Now let's have a look at the datasheet. Okay, now the timer we are going to cover here is timer 0. That is listed as an 8-bit timer as counter 0 with PWM. Now we are only interested in the counter bit of the timer for now. Some features it has 2 independent output compare units. It has a double buffered output compare register, clear timer on compare match, and auto reload. This is the one we are going to be using today. And then it also has a glitch-free phase corrected pulse width modulation or PWM. It has a variable PWM period and frequency generator, 3 independent interrupt sources, which is the timer overflow, compare match A and compare match B interrupt. And the main interrupt we are interested is the compare match A interrupt. Then they give us an overview of the timer, basically the control logic and whatnot of the timer. Now it says it's a general purpose 8-bit timer counter module, and then basically what we said above about the rest of the features. It allows accurate program execution timing, event management. That is what we are going to do specifically today, is event management, and waveform generation. And then they have a simplified block diagram over here. Then they have some definitions. Bottom means the low level of the counter, so 0, which they say here. And then max is the absolute maximum of the counter, so 0xFF or 255 decimal. And then top means when the counter reaches its top value. So you can actually in this timer edit what the top value is with the OCRA register, and that can also generate an interrupt for you. And then they give the registers. The registers we'll cover later when we get to the register sets. And then we have the counter clock sources. The timer can be clocked by an internal or an external clock source. The one we are going to be using is the internal clock source. The clock source is selected by the clock select logic, which is controlled by the clock select bits in the timer counter control register, specifically the B1. And then they give the count unit, which is an even more simplified version of the registers and how they work. The output control unit is what we are going to be using here. So the 8-bit comparator continuously compares the timer count register with the output compare registers, A register and then the B register. We are mainly going to use the A register to set the counter. And here they show a block diagram of how the count compare works. Okay, then we have the compare match output unit. We are not going to be using this as we only want an internal timer, but it's good to know you can actually use the timers to toggle 2 pins per, I think it's 2 pins per timer that you can toggle using the output match compare. And then we have modes of operation. We are only going to look at 2 of them. We have normal mode, which we are not going to be using. This is the basic mode where all it does is it counts from 0 to 255 and then it goes back to 0, and then it can generate the timer overflow flag for the interrupt. So you'll get an interrupt every time the timer counts all the way up to 255. Then we have the clear timer on compare match or CTC mode. This is the mode we are going to be using. We are not going to be using the outputs for the compare match. We simply just want a interrupt that ticks once a millisecond. In clear timer on compare or CTC mode, the OCRA register is used to manipulate the counter resolution. So you can set the timer resolution anywhere from 0 to 255. Right, this gives you more granular control control over how the timing is used. Then they have a timing diagram of how the pins will output and how the timer works. As the timer increases, then we have a compare match, and then the timer value goes down to 0. So this will count all the way up to X value and then reset the timer back to 0 every time there is a match. And you can see also here shorter intervals that the timer operates on. And then we have this formula over here. Now this is for the pin output frequency, and you can notice the 2 over here. This 2 is because we are running here for 2 cycles. It's because we have a repeating waveform for 2 cycles. So it will give us that will give us the frequency, but we need a timer, so we just have a 1x cycle. So we can get rid of this 2, and then we have our timing sequence. So in our case we're using a 16 megahertz crystal. Now if we do some formula manipulation after we remove the 2, because we want t, so we have our time will be equals to our prescaler, which is n times 1 plus OCR0n over FTL. Okay, and I've already calculated this out. Our formula would be 64, which is our prescaler over here, 1 plus 249 divided by 16 megahertz, and that gives us 1 millisecond intervals every time it compares. All the prescaler does is it takes your clock frequency and divides it, and that's how much a single tick will be. So the timer register will ink by +1 for each oscillator tick divided by whatever your prescaler is. And then we have the timing diagrams, which is basically what I earlier said about the prescaler. You can see here a prescaler of divide by 8. Here's the clock frequency, and then every 8 cycles we add max by 1. And you can see here with a prescaler of 1 we tick on every clock cycle. Now we have the register descriptions. Then our first register is going to be the timer control register A. Then we have bit 7 and 6 compare match output A, which is going to be how the pin functions for compare output match A. In a non-PWM mode it will function like stated here, and then for a fast PWM mode it's going to function like stated over here. We are going to have these as normal port operations, so timer does nothing with these pins. And as you can see, by default they are 0, so they're automatically in the state, so we don't need to change the values of this register. And then they continue describing how it works. Then we have bit 45, which is exactly the same as 7 and 6, except it is for output B. And we are also going to have this as 00, so we don't need to change the register values. And then we have the waveform generation mode. And now something to note here is the waveform generation bit 02 can be found in the timer control register B. So we have 2 bits in register A and then 1 bit that controls it in register B. So we have to split our settings accordingly. Here they have the different modes that we can set according to the bits. Now the only 2 we can set are these 2, and then W2 is set in the B register. So we are going to set up in CTC mode, which is 10, and then our top value is going to be OCRA, and then it's going to reset the timer. Then we generate an interrupt based on that. Then we have the timer counter control register B. We have the first 2 bits, which is force output on compare A and compare B. This basically just forces a high on the A pin or a high on the B pin. They function exactly the same. The highest bit for the waveform generation mode, which we discussed earlier, and that's going to be 0, so we actually do not need to touch the bit in the software. And then we have the clock select bit, and then we have all our settings here. We are going to go for a prescaler of 64 and our clock source as the chip oscillator, so it's going to be 16 megahertz divided by 64. Then we can also use external clocks, but that is out of the scope of the video. Then we have the timer counter register. This is basically the register that increments every time the counter ticks. So it has a range from 0 to 255, and you can actually preset this register to a value and then start start the timer if you have some specific use case for it. Then we have the OCR0A register, and this register sets the top value when the timer counter is going to be reset. OCRB we are not going to use. This is used in PWM mode. Then we have the interrupt mask register, which is by default completely 0. Then we have output compare match B interrupt enable. We are not going to be using this one, but that is basically when the timer compare matches the OCRB register, then it raises the interrupt flag. And then the one we are interested in is the output compare match A interrupt enable. So when the timer matches OCR-A, it raises a interrupt for us. Then we have the timer counter overflow enable interrupt. So basically when the timer counter reaches 255 and goes back to 0, that interrupt will be raised. This is actually useful when you have a dynamic output compare match, because if you set your output compare match lower than what the current timing value is, it will only activate as soon as the timer has overflowed. But we are going to use a fixed output compare match, so we don't need the timer overflow interrupt. So the only bit we need to set is this one. And then we have the flag register, which is automatically handled by the ATmega328P for us. Okay, so now let's get to the coding. Okay, so we have the code here. The code is very similar to the previous one. We have our UART initted. We are not actually going to be using the UART, but it's nice to have in. We have the ADC initialized, which we are going to use as our time base. I've created a timer 0 H file and C file. We are going to put our code in the .c file of the timer 0.h. I have a print buffer, just if I want to print out something. We have a 8-bit wide run variable, which we are going to use to display binary numbers on the port pins. We have half of port D set as output for 4 LEDs, half of port B set as output for the other half of the 4 LEDs, so we have an 8-bit output. Our UART is initialized at 9600. ADC initialized. We have enabled the ADC5 pin as an analog pin, and we select ADC5 as our conversion pin. Then we enable the interrupts. We send out the string via the UART. We clear the 2 port values. We OR port B with the run variable so that our LEDs are in 0 state as we start, and then we run and we increment. So basically it's counting in binary. So that's the base code setup. Now let's go to a timerhole.c file. Now the first function we want to create is void timer 0 init, and we have void as our input. Now the first thing we want to do is we want to set our mode, so that will be the timer control register A. We say that's or equals to, that is going to be 0B10 for the waveform generation bits, and that is going to be shifted by WGM, and we are going to shift it by those bits. So now we have the mode. Now the next thing we want to set is our top value, so that is going to be the OCR0A, and that is going to be equals to 249. So that is going to be our top value where our timer is going to reset. Set the control register B, so we take here and we change that to B, and that is going to be or equals to, since the entire thing is 0, we need CSS00, and we are going to bit shift by that. Now I need to look up the value for a 64 prescaler. That is going to be 0B011 for our prescaler value. Now this also switches the timer on. If this is 000, the timer is off and not counting. So as soon as you set the prescaler, it turns the timer on, so you need to preset everything beforehand. Then we go to our timer interrupt mask for timer 0. We say that is equals to 1 shifted by, we can copy the bit over from the datasheet. We can make that or equals. So now that we have the timer set up to tick once a millisecond and reset back, and also generate an interrupt for us, we say ISR. Then we go down and we find the interrupt vector for timer compare vect on A. So that will be this one. So we just copy over the vector, place that end, so our interrupt is now set up. Now for the interrupt, we make a volatile static uint32_t, and we call this millis, and that is exactly the Arduino millis that some of you might be familiar with. And we take millis, and every time the interrupt occurs, we just increment millis by 1. Now this will take around 52 days to reset if you run continuously, and I believe if you make it a uint64, which is not supported by this chip, it will run until the heat death of the universe. Then we create another function which is uint32_t, and we also call it millis. That is going to take in void parameters, and all it needs to do is return the millis_c value. And then something fancy we can do, we can say uint8 for our return type, and we say millis_end. That takes in a uint32 start time, and we give it a uint32, call it delay time, and all this does is return the millis function minus the start time, and we encase this in braces, and then we say if it is greater or equals to the delay time, just return the comparison for us. So this will return either 1 or 0 depending on what the evaluation is over here after the mathematics. Now we take our functions and we stick them in our .h file so that we can use them in our main.c file. Now we add 2 variables at the top. One is going to be uint16, call it ADC, and that is going to be equals to 0. Now this is going to be our value that we read from the ADC to determine the time delay. Then before we start our interrupts, we call timer 0_init, and that will set up the timer and start it running. And then we add another variable I forgot about, a uint32, and we just call it holder. This variable is going to hold the timestamp that we captured a value at. And just before we enter our while loop, we are just going to initialize our variables. So ADC is going to be equals to ADC_convert. So that will also initialize our ADC's internal circuitry and whatnot and give us an initial value for ADC. And we say holder is equals to millis. Alright, we take our entire blink code, we say if, and we encase that in a brace, and we do proper indenting. We take our function of millis end, we give it our holder time, and then we give it the amount of time we want to delay by, which is going to be the ADC value. And then after we have set the LEDs, we call another ADC conversion and we change the holder variable to the current millisecond value. And we just quickly program. Okay, now as you can see, we have the LEDs incrementing over here. I have the top LED. Just pull out the programmer. We have the top LED currently at maximum, but as I turn the pot, you can see especially the red LED, how it goes faster as we start ticking. Then we have a strobing effect as well. And as I turn it back, we have a slower blinking LED. Okay, and that's an introduction to using timer 0 on an ATmega328P. A like, share, comment and subscribe is always appreciated. The code will be on Git. Thank you. Have a nice day.